in. Our next speaker, Stephen Morgan. He's a security engineer and consultant, largely within the fintech industry. He enjoys long walks on the beach and getting security teams to fund application security. And he's going to tell us the many sins of Web3. It might be surprising, but do you know that many of the assertions made by blockchain advocates aren't entirely accurate? So we're going to look at some of the worst security offenses from a retired cryptocurrency early adopter. Over to you, Stephen.
Thank you. Oh, you can hear me. Hi, thanks for coming. My name is Stephen Morgan. Oh, shoot. Let's do this. Here we go. I'm a contract security consultant / penetration tester / AppSec engineer. In regards to cryptocurrencies, my experience goes all the way back to 2012 when it was actually still possible to mine Bitcoin with a GPU. I have the distinction of having lost at least 2 Bitcoin by reformatting a laptop, so thank you. When I jokingly told my wife about this $100,000 of lost Bitcoin, she did not laugh. The views and opinions in this talk are my own and do not represent those of my clients. But before we go much further, can I get a show of hands? Can you put your hand up if you've owned any cryptocurrencies? Yeah, that's pretty good. Can you keep your hand up if you've actually, so those might be on a centralized exchange. Can you keep your hand up if you've actually interacted with a blockchain? Like used a cold wallet or, like run a node, for example? Cool, all right, so I know who to avoid direct eye contact with. Cool. So what are we going to talk about? When people talk about cryptocurrencies, they tend to do it from one of 3 camps, the technical, financial, or political. Today we'll be taking a critical look at the technical aspects of blockchain products, the code, the network, and of course the security parts. I was motivated to give this talk because during the last peak when cryptocurrency prices were at an all-time high, I felt like what the influencers, the marketers, and the pumpers were saying about the technology and versus what the technology was actually capable of was a mile wide. So that's the theme of this talk, to explore the edges of the technology, call out the exaggerations, and the lies. So this may get spicy. What are we going to talk about? We're going to talk about decentralization. We're going to talk about censorship resistance. Gosh, yeah, that's going to be fun. Privacy, yeah, I know, right? Code is law, and I've got a fun surprise at the end. Hopefully there'll be time for questions, but I was over time every time I've done this. So, blockchains. Okay, before we go too far, I'm sorry, I need to lay some groundwork about what a blockchain actually is. If you're in this room, you probably already know the basics, so we'll just go over the technical details that are relevant for later in this talk. Full disclosure, we'll be mainly focusing on Bitcoin and Ethereum because they are by far the most popular. In this example, we're using Bitcoin, but at its core, a blockchain is a Merkle tree, a data structure of nested hashes. A block is a data structure that contains 10 minutes worth of transactions. We include the hash of the previous block in the current block's header, which is then hashed along with all the other metadata. This is important because if someone were to go back and change something in the previous block, that modified block's hash would now not match what was included in the following block. Thus, we can ensure the integrity of all the transactions from the start to the latest. To make transactions, we use a wallet application that signs a transaction. And the transactions themselves appear to come to and from wallet addresses. So pretty standard private, public key stuff. And that's kind of it. You see, the blockchain is just the data structure. It's just the state. And to find the balance of an address, we have to look through the whole length of the chain and calculate how many coins that address has received and spent. The main goal of Bitcoin when it was created was to avoid a trusted authority in the wake of the 2008 financial crisis. So the blockchain would need to be decentralized. Anyone should be able to get a copy of the blockchain, and anyone can be a part of the peer-to-peer network. Each node, as they are called, can request any part of the blockchain from anyone throughout the network. For example, I can request block 2 from Alice and block 3 from Bob. I'm able to validate that Alice gave me a genuine block if its hash is included in the block from Bob. Nodes are a fundamental part of the network, and as a decentralized peer-to-peer network, Bitcoin nodes make up to 8 outgoing connections and receive up to 115 incoming connections from other nodes and share the data like the addresses of other nodes, unconfirmed transactions, block headers, and the blocks themselves, using what's called a gossip protocol, meaning data will often be shared without asking for it. But a distributed blockchain where there is no gatekeeper would be absolute anarchy. How do we choose which block to generate the next block from? What's to stop someone from going back to change some old transactions, rehash all the blocks, and share them as if that's the real chain? We need a mechanism to slow down the network, prevent double spending, and to make it incredibly hard to rewrite history. They would need a consensus algorithm. To accomplish this, the creators of Bitcoin adopted the proof of work concept used in the anti-spam system Hashcash. Proof of work is a problem that the sender can only achieve through brute forcing and the recipient can easily validate. For Bitcoin, this problem was to find a nonce where the resultant hash of both it and the rest of the data in the block was of a sufficiently low value. Other blockchains use another method known as proof of stake, where the validator is determined deterministically but randomly and proportional to the amount of currency that validator has staked on the network. This method is significantly more energy efficient. As it turns out, mindlessly hashing through trillions of nonces for potentially no reward is extremely inefficient. It should be noted that these consensus algorithms are only necessary because the network is decentralized. If a network is controlled by a single entity or trusted parties, there is no need for a proof of work or a proof of stake. You would only go through this much effort to maintain integrity when centralized access controls are not an option. Let's finish off this refresher by talking about smart contracts. In 2015, the Ethereum blockchain introduced smart contracts, a mutable code that is essentially a series of functions and variables hosted by the blockchain. Developers can write contracts using the Solidity programming language, which is then compiled to bytecode and deployed to the blockchain where it gets an address. Users then call the RPC interface of a node to do something with that contract. What this usually looks like is that the smart contract is the backend to a traditional-looking web front-end, where the web front-end has libraries that do the translation for you. Whoa, we're going for time. See that? That wasn't so bad, was it? Cool. So that's the theory, right? So let's dive into decentralization, right? Decentralization is a core feature of every blockchain. But what is decentralization? Decentralization is actually a political term meaning to delegate away decision-making and authority to smaller factions within it. With blockchains, AWS defines decentralization as the transfer of control and decision-making from a centralized entity to a distributed network. Decentralized networks strive to reduce the level of trust that participants must place in one another and deter their ability to exert authority or control over one another. In theory, if one node on the network decided to change the rules, it could not affect the rest of the network unless other nodes chose to adopt these rules themselves. As a security feature, decentralization is a pretty good resiliency feature because we aren't dependent on a single point of failure. An entire continent of nodes could lose internet access and the rest of the network would continue processing transactions. At least that's the idea. And when I started describing my thoughts about decentralization and how it's been implemented, I kept referring to a popular blog post by Signal creator Moxie Marlinspike about his observations on the state of decentralization when he was working on several distributed applications. He states that even the term distributed application is a bit misleading, as there's nothing particularly distributed about them. DApps, as they're called, are just normal React websites that are usually hosted on traditional servers where some of the logic and some of the state are on the blockchain. While describing it, he has this quote. When people talk about blockchains, they talk about distributed trust, leaderless consensus, and all the mechanics of how that works, but often gloss over the reality that clients ultimately can't participate in those mechanics. He's not just talking about the front end. Let's talk about MetaMask. If you've done anything with a blockchain in the last several years, you will have heard of MetaMask. It is the singularly most popular blockchain wallet application out there. It is a client-based application that looks after your keys on your device and interacts with the blockchain on your behalf. MetaMask gained popularity due to its ease of use. You could run it as a browser plugin. You could use it as a mobile app. You could run it from home or somewhere else. And this is the problem. You see, blockchain networks have no concept of client-server. You are either a node and you are on the network, or you are not on the network. Nodes have their own networking layer, where they talk, have their own networking layer where they talk their own protocol on top of TCP using a dedicated port. Users usually use an HTTP-based RPC interface, which wallets use to transfer signed transactions to be transported throughout the network. But because of the nature of what is possible on this interface, it is strongly advised not to expose the RPC interface of your node to the public. So if you want to make a transaction, you either need to run your own node at your cost, or already know and mutually trust someone else's node. Blockchains are big. Bitcoin's is roughly 500 gigabytes, and the Ethereum blockchain is in excess of 1 terabyte. Because of the promiscuousness of the peer-to-peer network, running a node also consumes a lot of CPU and network data. Wherever you run a node, there is a cost associated. The most popular Ethereum wallet called MetaMask, Mist, actually required users to run a node in the background. MetaMask solved this problem by relying on what is called a node provider. Node providers are a thing I never thought I would have to explain. It's just so far from the principles of a blockchain when I started in 2012. You see, node providers are nodes as a service. There is practically nothing Web3 about them. They are standard HTTPS APIs. They operate the nodes and just return a standard JSON response to the wallet. The user still owns the custody of the private keys on their device, and signed transactions eventually get to the distributed, decentralized part of the network, but not before it goes through this intermediary. It's the node provider sending back information like your balance, transaction confirmations, and transaction fees. Most wallets do allow you to change your node provider. There's even a self-hosted option. But as Moxie points out, most people don't want to host their own server. These decentralized providers as your gateway to this distributed network is the equivalent of Chrome users having to go through Google servers to access the internet. The most popular node provider, Infura, don't share their metrics, but it is understood that the majority of calls on the Ethereum blockchain occur through them. MetaMask won against the self-hosted wallet option. The market decided that this was preferable because it meant that they could use the wallet on devices they couldn't otherwise. This suggests to me that decentralization is not a core value for the majority of users. Moxie says, partisans of the blockchain might say that it's okay to have these types of centralized platforms emerge because the state itself is available on the blockchain. So if these platforms misbehave, clients can simply move elsewhere. However, I would suggest that this is a very simplistic view of the dynamics that make platforms what they are. Node providers are centralized entities with centralized decision-making. They can choose to apply your transactions to the mempool. They can choose to sell your usage to a third party. And if they have an outage, you lose access to the blockchain. All examples of what you are trying to escape by using a decentralized platform. One of the funny things about all this is that Infura is as popular as they are because their nodes have a reputation for being very fast. When users send a transaction to a contract through Infura, actions are confirmed quickly. They can see those actions promptly on aggregators like Etherscan. These transactions are fast, not because of anything magical Infura are doing, but how centralizing their popularity is. You see, nodes can have preferences. With Ethereum, for example, you can choose to configure a trusted pair, which are basically sticky connections that nodes will hold on to for dear life. The reason your Infura requests show up faster is because many of those other services are connecting straight to Infura's nodes and not waiting for the information to propagate naturally like a real peer-to-peer network. It matters that a component of your interaction with the blockchain is centralized. For a given transaction, you cannot interact with the blockchain if one is censored. Let's have a bit of fun with this and formalize this into a fundamental principle. Let's call it Moxie's Law of Decentralization, because I'm sure he would love that. I had a bit of fun with this, I'm sorry. Here we have decentralization D, which is the minimum of the least censorship-resistant or least distributed component of a transaction. Put another way, we can say that your transaction is only as decentralized as its most centralized component. Obviously, decentralization means lots of things to different people. I went with distributed trust and censorship-resistant because I think it's the fairest definition for why you would use one of these platforms over a centralized one. Now, we could move on to softer centralized targets like non-fungible tokens or decentralized autonomous organizations. None of those words are actually what they are. But we don't have time for that, so let's go straight to a more challenging example and explore why I think absolute decentralization is a pipe dream. Let's talk about Bitcoin. As far as decentralized networks go, Bitcoin is doing pretty well. One of the challenges of a decentralized network is being able to manage dishonest nodes. Bitcoin actually handles this dishonesty on the network pretty well, with a component called Address Manager and several techniques to handle address poisoning. But how do new nodes connect to a decentralized network? BitTorrent networks, for example, usually rely on a centralized tracker server to maintain a list of peers. The answer for Bitcoin is, well, also pretty centralized. The Bitcoin network propagates by gossiping the locations of other nodes on the network. But when starting a fresh node, you need to know the address of at least one node on the network to bootstrap this process. Bitcoin Core does this through DNS seeds, a short list of 9 DNS records. These modified DNS name servers that return known healthy nodes in the DNS response. Oh, that's not very big. Overall, I think this is a cool idea, but 9 hard-coded records is a bit scary from a censorship resistance perspective. New Zealand, for example, has several examples of censoring DNS records. Not only that, but all it would take to delist these domains is for someone to fake a phishing attack and report it to the registrar. Well, okay, the core devs have thought about this and they have a fallback. If the DNS seed bootstrap fails, the node will fall back to a hard-coded list of known nodes called seed nodes. This time, instead of only 9, there are 512. Much better, right? Surely this is a curated list of trusted nodes. It would be really obvious if someone tries to undermine this list with their own malicious nodes, right? Well, actually, looking into the change history of this file, the list is completely replaced with every new version. It's being automatically generated by this Python script. This Python script is fetching the replacement list from a single DNS seed server owned by an ex-Bitcoin maintainer. So for a new node, 9 domains and a single person are responsible for ensuring that you get on an honest network and not a bunch of malicious nodes. It's not going to break Bitcoin, but it's not what I would call trustless. The Bitcoin developer problem is something usually glossed over by decentralization advocates. The Bitcoin node software is hosted on GitHub, and there are a grand total of 5 people with maintainer permissions to the Bitcoin Core GitHub repository. 5 people ultimately have the say on what gets merged into this decentralized network, and there is no public information on who currently uploads the compiled client to bitcoincore.org. But there are contingencies in place, you might think. It's open source. Pull requests are done in the open. If miners are unhappy with a change, they just won't use the new client. If you're worried about the integrity of the binary, Bitcoin supports reproducible builds, and you can check the signature against a published list of trusted users. The year is 2018. The block size war is over. Big blockers are licking their wounds, and small blockers are polishing their Lambos. An anonymous user responsibly discloses a bug that is causing his node to crash. The dev team review it and issue a fix within hours. The bug is labeled service denial. A new binary is made available the following day, which many operators promptly apply. Several days later, developers unpicking the issue discover the bug was also a massive inflation risk and would violate the sacred 21 million Bitcoin rule. The bug would have allowed someone to double spend within the same block, creating more Bitcoin in the process. Gosh. It is only when these developers voice their concerns that the Bitcoin Core team come clean about the full extent of the vulnerability. This is the perfect example of how the governance around the Bitcoin client is decentralization theater. Decisions can only be made collectively if they are done in the open. Ultimately, the bulk of users didn't care about the delegations and contingencies, they just blindly ran the new version. The Bitcoin Core maintainers have actually been pretty vocal about the need for more than one Bitcoin client. And there have been attempts by other developers to create alternatives. BTCD being the most used, running on a whopping 0.2% of nodes, making it 24th on the list of most popular Bitcoin clients after various versions of Bitcoin Core. Critics will argue that because the code is open source, all you need to do is submit your proposal and let the miners decide. But history has not been kind to this theory. None of the failed attempts to make changes to the Bitcoin protocol have had the support of the lead maintainer. Your network is only as decentralized as its least decentralized component. What does it matter if anyone can submit changes to Bitcoin Core if only 5 people can merge changes? What does it matter that the rest of the network is happily decentralized when your node is on a dishonest network? If users don't care about decentralization and would happily point their wallets to a centralized API, what does it matter that the state is decentralized? What does it matter that there are thousands of nodes on the network? If I wanted to if I only had to attack node providers to block the majority of users. Cool. Let's move on. Censorship resistance. Censorship resistance is not something mentioned in the Bitcoin white paper, but it was a popular talking point even early on. The EFF published an article in 2011 talking about how Bitcoin could be used to circumvent the monitoring of financial transactions and blocking of financial autonomy. And it's been a recurring talking point when trying to figure out a use case for cryptocurrencies. The problem is the majority of cryptocurrency networks are trivially censorable. But before we get into that, what is censorship resistance? Bitcoin.com, because we always go to .com, says that there are 3 pillars of censorship resistance. The immutability of transactions. As someone that has spent half of his security career working for banks, I would argue whether immutability of transactions is actually a desirable quality. But in the context of Bitcoin, I can understand. With no intermediary, can you imagine the challenge if the sender was able to return their funds? The freedom from confiscation. This one I can agree with. Self-custody is an attribute of cash, for example, that I find valuable. But even more so than with cash, self-custody comes with the liability of needing to maintain proper OPSEC. That is, you need to keep your wallet safer than that PGP key you made that one time and left in plain text on your laptop. This wallet is your life savings, and unlike cash, this key can be stolen remotely. The freedom to transact. Now, this is the one we'll be spending most of this section on, because it's often what people talk about when they talk about censorship resistance. The freedom to move currency without intervention by a government. Cryptocurrencies have a long and rocky history with censorship. In a recent example, the Tornado Cash smart contract was sanctioned by the OFAC for being a money laundering tumbler, which it was. Sanctions are a really serious thing. Violating these carries serious jail time. Concerned about violating this sanction, validators began censoring transactions from wallets associated with Tornado Cash. This graph shows the proportion of validators that stopped processing transactions from violating wallets. Right now, the proportion of censored transactions is somewhere around 30%, but it peaked at about 80% in November. Now for some real talk. Did you know that blockchains use the internet? And as governments all over the world demonstrate regularly, layers of the internet are censorable. Bitcoin nodes default to listening for incoming connections on port 8333. In fact, 95% of Bitcoin nodes on ClearNet are using this port. Ports, you should know, are famously blockable. I do it for a living. If a government were to mandate all ISPs block port 8333, your node can change their listening port, but it can't change the 95% of nodes that are now effectively blocked to them. And it's not just ports either. Hands up if you think the Bitcoin network is encrypted. Come on, come on. There's one person. The Bitcoin network is not encrypted. The integrity of the blockchain relies on signatures and consensus rules, so they don't feel the need to encrypt the traffic. Bitcoin nodes don't communicate with each other in HTTP. They use TCP as their layer 4, and they have their own custom protocol. One of the rules of this protocol is that every new message starts with what's called a magic byte, which is unique for each network. Because Bitcoin isn't encrypted, if a government really wanted to censor Bitcoin, it would be as simple as filtering every TCP packet that started with these bytes. You may be thinking, well, Bitcoin nodes support SOX proxies and the Onion router. Yes, they do. But consider whether more Onion nodes is actually desirable. There is no theoretical limit to the number of Onion addresses a single node can have. A majority Tor network is a Sybil attack waiting to happen. Besides this, most things support proxies. Saying that blockchains are censorship resistant because proxies exist is like saying that Xbox Live is censorship resistant. This censorability can be easily avoided by just using TLS and port 443. Privacy. Right, yeah. The God King Satoshi, in his white paper, has this pretty diagram showing how traditional payment systems maintain privacy by hiding the parties, whereas Bitcoin separates the identities from the transactions through the magic of Diffie-Hellman. The originator can remain anonymous. I've had a lot of people tell me that Satoshi never claimed that Bitcoin was anonymous. But Satoshi is quoted several times stating anonymity as a feature of the network. This obviously sounds ridiculous now, and apologists will say that he meant to say pseudonymous. But it's easy to forget that the supposed privacy of Bitcoin was actually one of the first use cases of the technology. These days, we have amazing block explorers that make trawling various blockchains seamless. But in the early days, it was actually really hard to trace transactions. The most popular early explorers were very slow and had practically no features. In security, we tend to treat privacy as protecting data from anyone not authorized to view it. Clearly, that's not possible with a public ledger if we want there to be transparency with transactions and the minting of new coins. For public blockchains, there is only really one way where you can remain anonymous. Mint the coin yourself and never spend it. You are de-anonymized if you buy it from a centralized exchange, purchase anything off-chain with it, use a node provider, use a wallet mobile application, connect your wallet to any other service. Public blockchains are anonymous if you never touch the sides. In fact, probably the only reason that Satoshi Nakamoto remains anonymous to this day is because he never spent any of the coins on his payment system. Yes, I said payment system. Researchers like Sarah McElhorn have taken this traceability a step further and developed clustering heuristic techniques to trace entire entities that would otherwise require monitoring millions of individual addresses. If you're a data nerd and would like to know more, I recommend her talk, Bitcoin is Not Anonymous, on YouTube. Just one more note on privacy. There are privacy coins that claim to have solved this problem, but as we'll get into in the next segment, the permanence of these claims is questionable. Code is law. That looks quite dark. Okay, so we've talked about network security and privacy. Let's talk about application security. Code is law is a phrase coined by Lawrence Lessig in his coin, Code and Other Laws of Cyberspace in 1999. Lessig at the time was arguing that code is a form of regulation that can have a significant impact on human behavior. What Lessig wasn't saying in his book was that code was a replacement for the law. Lessig was actually pretty explicit that ambiguities in the law can be a good thing, especially in a world of strictly typed languages. This nuance has been almost entirely ignored by many cryptocurrency enthusiasts who argue that the code that underlies a network or smart contract should be the ultimate authority on how that entity operates. Perhaps one of the more extreme examples of this are the Ethereum Classic adherents, who maintain a version of the Ethereum blockchain where a high-profile hack of the DAO contract in 2016 was never reversed. Falsification is a concept of scientific inquiry that is based on the idea that a theory or hypothesis should be constructed in a way that it can be disproven by evidence. One very important consequence of this principle is that a theory or hypothesis can never be proven to be true, because evidence that falsifies a theory can always come to light at a later point. Now, those of you that have been working in security for a while might find this concept familiar. How many times have you heard someone ask if something is secure? The best we can say is that the risk is low. And if you would allow me to coin another law, let's call this the securifiability principle. A system can never be considered secure. At best, it can only have no known vulnerabilities. The immutability of smart contracts in particular is a security nightmare. It means that your vulnerable application cannot be patched. You may have had it audited by Vitalik himself, but as we have seen time and time again, a new technique will be discovered that will change that. One example that I think encapsulates this dilemma is a recent hack on the money tumbler Tornado Cash again, in May of this year. This will get technical, but it won't be on the assignment. Tornado Cash had a DAO that controlled the governance of the system. On May 21st, a hacker executed a clever privilege escalation attack by exploiting the proposal process. The hacker's proposal was a contract that was practically identical to other similar proposals in that it had a deployer and a proposal structure. But it also had an extra feature. It had a self-destruct mechanism. Once the proposal had been passed by the DAO voters, the attacker simply deleted the contract. Now, normally this wouldn't be a problem. Contract addresses are checksummed. So if a hacker wanted to change the code and replace the contract, the address would change and the proposal couldn't be executed. Except the hacker didn't change the code. They redeployed the exact same contract. Deleting the contract had blown away the state, which deployed the normal proposal. With this part unset, the attacker could then deploy the malicious proposal. The malicious contract they pointed to gave themselves 10,000 governance tokens to wallets they controlled. The hacker owned the DAO. The response by the DAO to this attack was, well, nothing really. The hacker had abused the system fair and square. Code is law and all that. All the DAO could do was watch. The hacker ended up making off with around $650,000, which they promptly laundered through the tumbler itself. I like this example because it's the kind of clever hack we normally see outside of smart contracts. It's an example of something that would be almost impossible to think of when you are designing a system like this, where you thought you'd mitigated against an attack like this by tying the code directly to the contract address, but couldn't have foreseen how different systems would interact with each other to be exploited like this. Examples like this are everywhere in the realm of smart contracts and the blockchain in general. Oh, too early. And it isn't without a sense of irony that one of the best solutions this space has come up with to combat this is a centralized repository of known malicious contracts. But by the same token, relatively speaking, there are significantly more successful scams operating outside of cryptocurrencies, just by the nature of the number of potential targets. There are, however, some compounding factors that perhaps explains why cryptocurrencies are considered so vulnerable. The first one is incentive. Responsible disclosures for vulnerabilities in non-blockchain applications occur every day. But it's also true that vulnerabilities in regular applications just don't carry the opportunity for the researcher to earn thousands to millions of dollars if they chose to exploit it instead. The immutability of the blockchain is another compounding factor, as there is absolutely no recourse to recover your funds when you do get scammed. It's fair to complain about the payment card industry's 3% tax, but at least some of that goes towards not leaving you out of pocket. An underrated factor is the nature of smart contracts fees. Deploying and running smart contracts on the blockchain is not free. The fees you pay is proportional to the function's size and state that ends up on the blockchain. These fees aren't just paid by the developers to deploy the contract, they are paid by the users of the functions as well. This does two things. Firstly, it pushes a lot of the functionality off-chain. Take the most popular NFT platform, OpenSea, as an example. Their much celebrated profit sharing where a proportion of the funds is shared with artists is not actually occurring on-chain. Secondly, it means that developers are incentivized to be as concise as possible, using things like third-party libraries to do input validation, or relying on frameworks to delegate away all the primitive juggling is just not desirable. What this results in is code with the perverse incentive that it costs money to be secure, where every variable check and every if statement costs both you and your customers money. The last and most important factor is complexity. In case it wasn't clear, in the Tornado Cash example, blockchain clients and smart contracts are complex systems. It is inevitable that something will slip past a developer, and the chance of this occurring only increases with new features. It's not just developers that suffer this complexity. The average user of these systems is expected to be a technical, financial, and political expert. They need to be capable of self-auditing smart contracts, to have opinions on complex financial instruments, and to have OSN skills that will allow them to investigate the trustworthiness of project owners. And I think this is really the problem, my problem with all the talk around cryptocurrencies. And this is firmly in the my opinion category. But decentralization comes with trade-offs. Any way you try to cut it, decentralization is inherently more complex for the average user. This is the opposite of usability. Usability is a security feature. It means users are less likely to make an unintended mistake. Pushing this increased overhead to your users means your technology will never become mainstream. You need to pick a side. So we've talked about problems in the story about blockchains: decentralization, censorship resistance, privacy, application security. But technology can have problems, right? I mean, look at Active Directory. What's the big deal if the tech has a few quirks, right? Maintaining the Bitcoin network consumes as much energy as the nation of Kazakhstan, a country of 19 million people. A single Bitcoin transaction has the same carbon footprint as 840,000 Visa transactions. As alluded to in the beginning of this talk, proof of work as a consensus algorithm is criminally inefficient by design. We've spent decades of technological process trying to minimize consumption to the point where we can walk around with a computer in our pockets. Why do we think it's okay for Bitcoin to take this progress away? So my question to the people that put their hands up at the start of this talk, is it worth it? Is the gambling worth the enormous waste this game produces? So if you decide that crypto is fun and you want to keep playing, I encourage you to choose tokens that don't use proof of work. I said there was a surprise, didn't I? At the start of the talk, I've said that. You see, I had to do a lot of digging into the Bitcoin source code for this talk, because it turns out that, yeah, the information publicly available is unreliable. While I was digging, I found a feature that I had never heard of before. Did you know that Bitcoin core nodes have denial of service protection? Not just any kind of DOS protection. Early 2010s DOS protection. In 2011, Satoshi had implemented a system where each node would automatically block IP addresses that send malicious-looking packets. This system was called discouragement and would block the IP address for 24 hours. Knowing of reputation-based firewalls inadvertently blocking entire corporations' internet access and that IP addresses can be spoofed, I needed to know more. I was intrigued. When an IP address is discouraged by a node, several things happen to the nodes on that IP. For non-listening nodes, that is, nodes that don't expose their listening ports and thus aren't that important to the health of the network, they are priority kicked by nodes that have discouraged you. Nodes only allow a maximum of 115 incoming connections, so your connection to an effective node would be short-lived. The story is even worse for listening nodes on discouraged IPs. In addition to what happens to non-listening nodes, affected nodes will now not connect to you and will not share your address with other nodes. This got me thinking. What would happen if I recursively spoofed the IP address of every node in the network? Getting every node of the network discouraged by every other node. I did this too many times. Hang on. This would take down the entire network. Listening nodes would not connect to other listening nodes, nor would they gossip the address of other listening nodes. The network would cease to function. Sorry, this idea was short-lived because a full TCP handshake was needed, and I'm not an ISP. So I lowered my ambitions. What if I just got my IP discouraged by the network? That's at least something, right? After all, it's the IP address that is banned, not the node. If I was to do this from home without a static IP, this would get all the nodes behind my ISP CGNet discouraged. If I was using a commodity VPN, a Nord or whatever, this would get all the nodes sharing this VPN's IP address discouraged. If I did this through Tor, this would get all the nodes on my exit node's public IP discouraged. If I did this from the same IP as a major Bitcoin Bitcoin mining operation, you get the idea. I bet some people would be pretty upset if someone was to make a tool like this. So that's what I did. And MaxiBan was born. I've released it on GitHub for everyone to enjoy. MaxiBan will pull down the latest list of known Bitcoin listening nodes, handshake with all of them, and send a faulty header, which will get your IP address discouraged by the entire Bitcoin network. You just need to set up a cron job to do it every 24 hours. Don't worry, I did responsibly disclose this. I emailed my findings to Satoshi, but he didn't reply. For those interested in finding more about MaxiBan, please have a look at the GitHub repo. I had a lot of fun with the FAQ. And thank you.
We have time for maybe one question. Well, I'm sure everyone's going to go and try and MaxiBan.
Awesome.
Thank you very much.
Thank you. Ah, yep. Awesome.
Cool.
Yeah, thank you. Cheers.
Thanks.